Hi, and thanks for joining me in this discussion of fronts. This is the second in a series of videos about fronts. We're working our way through the definition of fronts. The definition is that a front is an elongated zone of strong temperature gradient, strong static stability, and also strong cyclonic vorticity. In the first video, we looked at what we meant by a zone, why fronts are zones. In this video, we're going to look at temperature gradients. When we say fronts are zones of strong temperature gradient, we're looking at how temperature changes over a given distance. That's what we mean by temperature gradient. And the gradient, or the change in temperature, occurs ahead of warm fronts and behind cold fronts, which can be somewhat confusing. Most people understand the concept of temperature change behind a cold front, but ahead of a warm front? That actually does happen. This is a representation, looking down on a weather map, of what a warm front and a cold front temperature gradients would look like. And you notice that each one of those red lines represents isotherms. We have the first one, the 0 degrees Celsius, and then also 5 degrees Celsius and 10 degrees Celsius. So notice that the temperature lines pack right behind the cold front and out ahead of the warm front. And that's where you see the change in temperature, or the temperature gradients. On either side of the front, behind the zones, or ahead of the zone of temperature change, we see more uniform temperatures. So we call these sectors, and where the warm is located, we call that the warm sector, and where the cold air is located, we call that the cold sector. Perhaps maybe you remember this from your basic meteorology class, that the warm sector is out ahead of the cold front and behind the warm front, and the cold sector is behind the cold front, but a good distance away from the cold front, because just behind the cold front, that's where you see the change in temperature. Here's an example of a day where we have an occluded front and a warm front and a cold front across the United States. This occurred in 2020 in October, and this produced quite a bit of snow in Colorado and also through Utah and Wyoming. And it was a very deep pool of cold air. You can see the surface positions of the warm fronts and the cold fronts and the occluded front. This is what the surface looked like with a temperature analysis. So these red lines represent isotherms. The isotherms are drawn every 2 degrees Fahrenheit at the surface. And you can see the packing of the isotherms right behind the cold front across Nebraska. You see it kind of gets a little bit more diffuse with the occluded front up through South Dakota and North Dakota and Minnesota. But notice where the warm front was located. The warm front was located across Iowa and also Illinois. And out ahead of the warm front, you can see a strong change in temperature, a temperature gradient. Behind the cold front, well behind the cold front across Wyoming, you don't see really strong temperature gradient. That's the cold air. And in the warm sector, out across Missouri, Oklahoma, Arkansas, you don't see a very strong temperature gradient, and that's the warm sector. You also see temperature gradients higher in the atmosphere. You can see them on the 850 millibar map, the 750 millibar map, and sometimes also on the 500 millibar map. Temperature gradients with fronts do extend through the atmosphere, but remember that fronts slope, so you won't find the position of the 850 millibar front right on top of the surface. It'll slope a little bit with the front. Here's an example this is the case that we just looked at, and we saw that there was a strong front across Nebraska, cold front, and actually this does show up pretty well on the 850 millibar map, and it looks like there's really not a lot of slope. But then you have to realize that across Colorado, 850 millibars is below the ground. So it's really hard to get a good analysis across Colorado and Wyoming because we don't have any temperatures. But you do see a pretty strong front across Nebraska. And then this is a little bit higher in the atmosphere, and these stations are showing up, except for Denver. No, Denver is showing up, but you do see that there is a strong temperature gradient, and the gradient does exist across Nebraska, Colorado, even South Dakota for that matter. Notice that the warm front is a little bit more diffuse, and you see the warm front kind of across Iowa, Wisconsin, perhaps, maybe even Illinois. If we send up a radio sonde through the cold air and also the warm air, we'll get, of course, a trace of temperatures. And that's what this represents. This is a cross-section across the front with colder air to the north and warmer air to the south. Notice that the front is sloping towards, of course, the warmer air, with the front sloping back over the cold air. The front, as we discussed in a previous video, is tropospheric spanning, which means that it does meet up with the tropopause. And you can see the tropopause is lower over the cold air up north and higher over the warm air down south. Notice also that the temperatures with the radiosondes in the colder air, of course, colder temperatures are closer to the ground. We have minus 10 degrees Celsius very close to the ground, whereas in the warmer air, you would find minus 10 much higher. Or for that matter, pilots are familiar with the freezing level, and in warmer air, 0 degrees Celsius will be found higher in the atmosphere than in the cold air sector. So if we drew lines or isotherms across the front, remember that in the cold air and the warm air, the temperature really doesn't change all that much in those sectors. In other words, the cold air is cold and the warm air is warm. You might see a little bit of sloping, and you do see that going from the south to the north. What you would expect is the isotherms to slope down a little bit, and then you expect the same thing also in the cold air. But where the front is located, when those isotherms meet up, notice that there's a jump in height. And as a result, those isotherms actually go vertical. And that's kind of a strange thing to see at first, but if you think about it, when we fly an airplane or drive a car from the south to the north, when we go through the front, we notice a rapid change in temperature. And that's what we're seeing on this cross-section, a rapid change in temperature across the front. In this case, the airplane, as it flies through the front, over a very short distance, it goes from minus 10 on the south side of the front to minus 20 on the north side of the front. And then in the cold air or in the warm air, you don't see really big changes in temperature as the aircraft flies along. So, of course, the strongest temperature changes will be experienced near the surface of the Earth. That's where the ground heats up and cools. So you will see very strong temperature gradients near the surface. And as you go up through the atmosphere, the temperatures weaken with height. Also, another question people ask is, what type of front were we just looking at in this cross-section? Well, it depends upon which way the front is moving. If the cold air is overtaking the warm air, then it's a cold front. If the warm air is overtaking the cold air, then it's a warm front. So that also shows up in the slope of the front. Here's an example. If we have warm air overtaking cold air, of course that's a warm front. The warm air is moving up. Remember, though, that warm air tends to rise. Warm air is less dense, so the stronger push of the front will be at higher altitudes and not at lower altitudes. So the surface position of a warm front doesn't move very fast, but the upper level position may move a little bit faster. Likewise, cold air tends to sink. It's more dense, so it'll stay closer to the ground. And if it's pushing towards the south, towards the warm air, you'll notice that friction kind of slows down that cold air push, and as a result, we get a little bit of a steeper front near the surface of the Earth. Well, that's about all we have for temperature gradients. In our next video, we'll look at static stability.